Okay, so we're going to start with example 1 in the notes. And this one, the context isn't as sort of rich as it might be for some others. So here there's no real picture to draw and not a lot really to figure out as far as like the equations go. But this is a good example to start with because it'll outline the process of what we're going to do. So the task is to find two positive numbers when we know the sum of the numbers is 60 and we want to maximize the product, right? We want the product to be a maximum. So this is telling us that the target function is going to be the product of the two numbers. And then we'll have an additional equation involving the sum of the two numbers, and that will be our constraint. All right, so let's start with the constraint. We're told that the two positive numbers have to add up to 60. The sum is 60. So we have x plus y equals 60, and this is the constraint. Right, we're not finding the biggest possible product of any two positive numbers, right? That would not have a real answer because you could make it as big as you want. We're looking for the highest possible product of two numbers given the restriction or constraint that they add up to 60. Right? And that turns it into a problem we can actually solve. Okay, the product of two numbers means you multiply them together. And so we're going to have our product, just call it P, is x times y. Right? Our two positive numbers are x and y. The sum is x plus y. We know that has to be fixed at 60, and the product is x times y. We're trying to maximize that. So here's an example already of a target function. That's got two variables in it, and we don't know what to do with that yet. So instead of trying to figure out what to do with several variables, we'll turn it into an equation with one variable. We use the constraint to do that. So we're going to solve for y in terms of x, just by subtracting x from both sides. And then we're going to put y in terms of x into the target function. Right? So because of the constraint, I can write y as 60 minus x, and now the product is x times what used to be y, but is now 60 minus x. So this is our target function. And if I multiply through, it looks like 60x minus x squared. So that's the thing we have to maximize. So take the derivative, figure out if there are any places where it doesn't exist, set it equal to 0 and solve, and then test what you get. So our derivative is going to be, well, derivative of 60 times x is just 60. Derivative of x squared is 2x. This exists everywhere, so we're only worried about places where it might be 0. And so we're going to get x equals 30. That's our only critical point. So it's the only thing we have to test. And I'm going to check whether it's a max or min by taking the second derivative of p and using the second derivative test. So the second derivative is just minus 2. Right? The derivative of 60 is 0. Derivative of minus 2x is minus 2. This tells me the concavity is negative for the entire function. In other words, it's concave down for the entire function. And therefore, since this is negative, x equals 30 gives us a max. All right, so the second derivative test says this is a relative max because we have concave down, right, at the critical point. And because it's the only critical point and the function is concave down everywhere, we can actually go a little further and say that this is an absolute max. Right? There's no other point that we could check. the function just continues down for all values of x. So x equals 30 is our absolute max. If x is 30, then the other number y, which is 60 minus x, is also 30. And even though it's not asked for in the problem, the maximum product would then be 30 times 30, which is 900. So if you know you have two positive numbers that sum to 60, the largest possible product is when you divide it evenly, and you take 30 times 30 to get 900. Okay? So that's our first example. There's no real context to tie this back to, or no units or anything, so we're okay with how we've left this one. Right. Now we'll move on to example 2.